on atomic scale modeling, nano material, nano device calculation. We have a nano academic technology partner that provide atomistics, nanoscale, crystal material, and device simulation while using density functional theory and perturbation with quantum transports calculations. So at micro level, this Fluxim is one of the partner where you can simulate a micro level device structures, including the array and PV modules applications. For atomic based material and device simulation, we have this nano academic technology. Today we will focus about this Fluxim only. So I want to introduce about our parent company, that's name called Fluxim. Flux, that stands from Flux. So Fluxim is basically a Switzerland based company which provide the software for simulation as well as hardware, where you can also characterize some different properties of your devices. I will tell you how. So this is basically provide the software and hardware for R&D industries all over worldwide. Those who works on OLED, display, lighting, solar cells in industry as well as academic institute, both. So the company was started from Zurich University of Applied Science in 2006. So around 17-18 years of development in this particular optoelectronics research. If we talk about the software for the simulation purpose, that is called SATFOS and LAOS. You can see these are SATFOS and LAOS. These are two products. One is called SATFOS, that is a competitor of Escapes Bundy, but more advanced features as compared to the Escapes Bundy because it can perform unlimited number of semiconducting device simulations. So for one-dimensional simulation, this allows this SATFOS product is there, which can simulate the perovskite, tandem, thin film, or organic solar cells application at micro level, one-dimensional structures for incoupling, outcoupling, and light absorbing applications for optoelectronics calculations, optical analysis, and electrical analysis. If somebody want to work on large area devices where there are some the thickness of the device solar cell is in millimeter or micrometers in higher range side, then this LAOS product will be very helpful for large area organic semiconductor device application. And what are the problems that will be overcome by using LAOS that coming through the SATFOS or Escapes Bundy? Because Escapes Bundy and SATFOS both are one-dimensional simulation software at a cell level, not at micro level or large area devices. At particular cell level simulation, Escapes Bundy or SATFOS is more good enough. But when you go in the advanced levels for large area where the size of your device increases, then you require some more tool which can handle the complex geometry of your device structure, of your electrode structures, or the losses, whatever happening in your device, that should be overcome. That's why this LAOS software will come in the picture, where large area devices simulated and the losses will be there in one-dimensional tool that can overcome by using this LAOS softwares. So this is a brief idea about SATFOS and LAOS. We'll go to the detail in one by one. And since the company not only developed the software, because software is based on theoretical predictions on the basis of model equations, parameters, it will solve the equations based on theoretical assumptions and it will plot the near to the experimental characteristics. So that before going to the experimental in the lab or going to the fabricate your device, synthesize your material, you can virtually simulate your material behavior, material characteristics, and then you can go for the final experiments. So we have also supplied this hardware. You can see in the red color, PIOS, pillows, Letos light. These are basically a equipment where you can characterize your solar cell electrical and optical characteristics. Let's suppose you have a sample of solar cells and that sample of solar cell you want to study what will be the current voltage characteristics, what will be the that LED cases, electroluminance, photoluminance, spectra. So for electrical characterizations, impedance measurements, transient measurements, characteristics, then this PIOS is useful. And for electroluminance, photoluminance, goniometer, then this flows is useful. For stability analysis of your solar cells, let's suppose you want to study the perovskite solar cell degradation analysis or how much the solar cell is stable, then this Litos light are very helpful, where you can also measure your characteristics of your device applications. So these are equipment where the electrical optical emission property can be measured on the experimental levels, and it can also match with the theoretical simulations. So software and equipment both are aligned to each other so that you can find either you can go directly with the equipment for the characterize your device application, or you can perform your virtual simulation by using the software, and then based on the final your accurate input characteristics you can fabricate your device. So these are all single all-in-one measurement platform with integrated analysis software for electrical optical device characterization, parameter extraction, and model. Whatever model you have applied, you can also validate by using the product that Fluxium supply. Now, if we talk about this, since you are will also attend or maybe attended Escapes Bundy. Escapes Bundy is also very good tool for open source simulation, where this kind of commercial tools are not available in the educational institute. Then Escapes Bundy is good. But as compared to the Escapes Bundy, we have this SatFOS software for one-dimensional simulations, where perovskite, tandem, thin film, organic, similar functionality as compared to Escapes with advanced advantages as well. In terms of number of semiconducting layer, unlimited semiconducting layers at cell level, it can be simulated by using this SatFOS. Multiple parallel transient simulations, LED simulations, emission calculations, and with different state of art mobility models are implemented, and some ion transport models are included, including with the charge transports as well. So charge transport with ion transport, anion and cations, but will not be there in Escapes Bundy. Transient will not be there with Escapes Bundy, and unlimited number of semiconducting layer. Let's suppose you want to simulate a 10 layer, 20 layer, or tandem solar cell where there are so many layers. Then Escapes may be able to not simulate more than 7 layers. That's why this SatFOS can be helpful in this particular cells one-dimensional applications. So this is a brief idea about SatFOS also. Since this webinar was totally focused on Laos, then so we will discuss about this Laos software. Laos is basically if you want to simulate the device where the area of the device is bigger, okay, and in your small devices there are losses are happening, but it could be a temperature losses where you are applying some temperature on your device. It may be get heated or overheated. So that kind of losses can be overcome, or some electrical losses may be there. The losses may be due to the geometry of your electrode, wherever you will apply some biasing on the terminal. Suppose you have a solar cell, P and junction is there, and you fall some spectrum, light spectrum, EM0, EM1.5, or whatever the spectrum you fall. And whenever you are measuring its characteristics, there may be some losses are there. It could be the electrical losses, it could be the thermal losses, heating, or optical losses. So in this case, and for crosstalk applications, pixel, crosstalk, AM, OLED, in nowadays in you maybe heard about active matrix, organic light emitting diode, or quantum LEDs. So this software can help you to simulate the crosstalk, array, RGB, or some large area PB modules, multiple cells can be connected together and you can simulate its behavior. So this software is to design and optimize the large area devices. It is based on two-dimensional model plus one-dimensional model. Two-dimensional where there is a FEM is there, finite element method option is there. You can generate your mesh, triangular, hexagonal mesh can be generated, and you can optimize your device structure based on different certain input parameters. Input parameter in the sense whenever you simulate your device, you may have some different thickness, maybe different doping concentrations, or maybe some different work functions, or maybe a couple of other input parameters. So you can optimize your devices and you can simulate it. And the losses are happening in your device. It could be by overheating of your device. That overheating can be overcome by using thermal module. Electrical module is there where you can simulate the characteristics of large area device, optimize your electrode design. The electrode design may having pentagonal of mesh size, hexagonal type of mesh size, or maybe some different geometry. Due to the geometry problem, some losses also happen. And how we can optimize the more greater accuracy to increase the greater accuracy to optimize your device structures. Optimization is very important so that you will reach at your final approximations output. So that's why this electrical module is there. So software is divided in module, electrical module, thermal module, optical module, whatever module convenient for you that can be planned. So basically for reduction of electrical losses, non-ideal effect, maybe in LEDs or solar cell, maybe some unknown things may be there, which is affecting your device efficiency. So this software will try to get it converge quickly, and it will try to produce more accurate characteristics of your device based on theoretical assumptions. It will understand the electrical crosstalk in RGB OLED pixel array. Multiple arrays can be created and you can get it simulate. And thermal module, which can also coupled with electrical. So electrical module, thermal module, both can be independently, it can work, or it can be connected together so that simultaneously you can overcome the electrical losses as well as the thermal losses. So the thermal module, that is a two-way interaction between the heat generation and electrical properties of semiconducting devices. It will calculate the temperature distribution. Whenever you apply some temperature in your device, the distribution will be happen. It can measure or calculate the temperature distribution in your solar cell or OLED with different standard conditions. And it will also explain the non-ideal IV characteristics, whatever due to the electrothermal coupling or any other regions. So that's why electrical losses, thermal losses, or electrothermal losses can also be overcome, including independent optical module is there. So this optical module where it contains the powerful 3D ray tracing module, where whenever the rays are entering on the device, it will capture the device how the rays are diffracting or refracting, or how much the light get absorbed by your device. So that optical analysis or remove some optical losses that can also be overcome by using this optical module. So software is divided in module, whatever the module, maybe you are working on only electrical part initially, only electrical with the thermal as well, or all of them together can also be taken. Now you can see this is standalone 3D optical element with their contribution of the device. It can also help to simulate the optical crosstalk in OLED display. It can be coupled with the set force to analyze OLED and PV with complex light outcoupling geometry. So this allows is two-dimensional large area device simulation software. If you already have the results from one-dimensional tool, or let's suppose you have a IV characteristics from other source, that IV characteristic data you can upload, you can import in this Laos as well. So that's why it is telling the set force results can also be imported. Even in other third-party output. Let's suppose you have a current voltage characteristics you want to upload and you want to compare with your one-dimensional or any other tool with this LAOS for large area device application tool. So that's why this software is divided, and it's a brief idea about the LAOS. Now let me discuss about each module. As I told you, there are three modules: electrical module, thermal module, and optical module. So this electrical module is basically a 2D FEM finite element based module which will solve the Ohm's law in two-dimensional in two electrodes, top and bottom electrodes. And it can also coupled means it can integrate with one-dimensional Escapes Bundy or Satforth tools. So 2D plus Bundy FEM simulation, that's why we have called in the beginning. Satforth was only for one-dimensional. This software for two-dimensional plus one-dimensional, which can solve the Ohm's law in two electrodes. Now this LAOS simulation with electrical module can use to optimize the geometry. Either you are working on emissive devices or optical devices without costly or time consuming process of device fabrications. Sometimes what happen, the geometry which you created on top of the surface, and that geometry may get your light back in the environment. So that's why this software can help you to judge, to understand that how much light get absorbed by your device by using this module, and you can find the electrical characteristics. Now as you can see, this is a reduction of electrical losses. So optimization of device electrode in OLED or PB, potential distributions at top electrode that can be optimized with the distinct metal finger grid. Metal finger grid can be created on top of the solar cell. I will show you in the coming picture. You can simulate the light, LED lighting panel or large area devices. As you can see, this is a 2D FEM based device structure where you can define some cathodes, boundary conditions, Bundy coupling, slow loss are there, input quantity, and you can calculate the current density potentials. So anode boundary conditions, some cathode boundary conditions, you can define and integrate 2D plus Bundy FEM simulation and find the current density potentials. You can see this is electrical potential, which you can see in the screen, and IV characteristics. So this is some characteristics channel visualization data which you can visualize once you find some losses, electrical losses or different losses in one dimensional as well as in the graphical representations. Now in this same electrical module, if you want to optimize your device, so metal finger grid option is there. So you can create multiple metal finger. Metal finger in the sense there is some strip line on your solar cells are there. That strip line geometry can be created in the tool and it can also get it optimized. So that's why this metal kind of finger grid can be created or added to the transparent electrode of this photovoltaic device that will help to improve the conductivity or device efficiency. In coming slide, I will show you how the metal finger or different kind of grids can be created on top of the solar cell structures. So you can choose the different material, whatever the material you want to use for the metallic or even for the semiconducting layers. So there are two major important parameters for this to choose the type of electrode with respect to its transparency and conductivity. So we can easily select whatever the parameter, whatever the material, and LAOS can also use to produce a chart of best materials for photovoltaic depend on device size. So you can optimize with minimum value, maximum value, and run the job. You can set the minimum parameter of particular value, let's suppose temperature, potential, thickness, or whatever the current it is there. Minimum and maxima it can set, and you can run the job. It will plot the characteristics on each and every point voltage or whatever the input you have given. Now you can see this is maximum output power watt per meter square, and with respect to metal finger width grid. So losses are happening due to low global conductivity. Metal finger optimal bits power are there, and in this particular region why the losses are there. So losses are there due to low global conductivity and loss due to shadowing of the effect. So that's why this potential graphical representation can be visualized, and it will help you to optimize or to maximize your output. And accordingly, the sample 1 and sample 2, there are two samples taken. Sample 1 red graph and sample 2 blue graph. And accordingly, this electrode side length of the electrode is taken in centimeter: 0, 2 centimeter, 4 centimeter, 6 centimeter, 8 centimeter or 10 centimeter. And maximum output power, this is maximum output power that can be calculated. Accordingly, you can judge that how much light that reduction in the losses is happened. Now, if we talk about some different more models are there. So there is some non-ideal effect models are there for solar cell and LED, both application. So this electrical shunts are there, which are unwanted short circuit that can be happened by this non-ideal effect that between the two metallic electrode, and that will decrease the efficiency of the device. So unwanted short circuit are happening, that electrical losses are happening due to not unwanted short circuit of the device structures. So that non-ideal effect can also be overcome. This laws can also simulate the distribution of your potential and current inside the whole device. At what particular regions you are getting the maximum current, or which particular region you are getting the less currents. So this kind of things can be done, and this result can be correlated. Non-uniformity of device can be simulated, and now you can see in this picture. Understanding electrical crosstalk in RGB OLED pixel array. So this pixel in OLED display can be electrically coupled through the electrical lateral leakage current of common layer, or that will call, this effect will call the cross strike. Okay. So adjacent pixel in OLED display that can electrically coupled through the lateral leakage current of a common layer. That is called, this effect is called the crosstalk, and results in unwanted light emitting from the unaddressed pixel of different colors. You can see this one, this image, where red, green and blue, these are three different colors are there, and these are some different pixels. The square pixels are there. So this effect, this pixel which is having with different colors, and that will reduce the constant ratio, and that can determine the color gamut of the device. So Laos can achieve the quantitative understanding of electrical crosstalk in OLED. So let's suppose you can see this RGB pixel array device structures, and in this pixel device structure can be created in this Laos. You can create the geometry in rectangular or different other shapes are there, and find this array can be created, and once you will simulate this device structure, crosstalk currents can be generated, and you can find the potential and other characteristics. In the demo part, I will open the software, and in the software as well, I will show you live. And after this presentation demonstration, those who is having the license of this Laos, because 50 license is given to the institute, and you can also explore it. If you have any problem during the exploration, you can let us know. We can also help you technically. Now, whatever the results are coming by the virtual simulation through the Laos, are they validated? Are the results are reliable? So that's why we provide the reliable characteristics of your device structures. So this Laos can do the simulation successfully on different experiments we have tested. So you can see this is one paper where inhomogeneous luminance in organic LED related to electrode resistivity that has been reproduced. So luminance is calculated You can see this experimental red graph, this particular 0 to 15. You can see this Laos results, and this is experimental result, red one. So around 95, 96, 98, 92% accuracy we can predict based on theoretical models. And then you can go for the fabrication, for the characterize based on your final material input parameters. That can save your time, that can save your money, and that can save your that different iterations that you will going to perform on your materials. So the material or device, it could be wasted if you are not getting the reliable results. So that's why this simulation tool will help you to understand as a theoretical aspect how the behavior of the device will be changed on different in which different conditions. Now I have explained about the thermal module. Sorry, I have explained about the electrical module. If we talk about the thermal module for heating or temperature analysis, then this thermal module is there. So this thermal module can also be integrated with the electrical module so that electrothermal module property can be calculated. So electrothermal coupling, which will help you to simulate the two-way interaction between the heat generation and the current flow. It will calculate the temperature distribution in your whole device. Let's suppose you have a sample of the solar cell. You applied some biasing on the electrode contact, and due to the current will flow inside the device, and whatever the potential temperature distribution in your device, that study can also be understood. So in this different scenario, the current flowing inside the solar cell or OLED, that will heat up the device because of Joule heating. Laos can calculate the position dependent temperature in the device and correlated potential with different distribution of temperature. Heat generation and current flow in two-way interaction, that can also be simulated. Non-ideal IV characteristics in OLED and solar cell. In this two-way electrothermal coupling, heat is generated due to the current flow, the electrical conductivity inside the semiconductor stack, that will increase the rising temperature. Now with this two-way electrothermal model, this Laos can calculate the temperature distribution operating and different shape, either it could be S shape or L shape, whatever the shape. Characteristics, IV characteristics, positive feedback from increasing temperature, increasing current, increasing temperature, that kind of study. Current density, that can increase when you applied voltage decreases because the temperature increases at the same time. You can see this is some finger grid geometry that has created, and this is a hexagonal type of metal finger grid which is created in the geometry builder and imported in the tool, and then applied some different model input parameter and do the simulation and plot some characteristics based on different voltage wise. The current density is plotted on different valence band gap of the materials. So that's why this is two graphs that will represent for thermal module heating related characteristics. Now the third module is called optical module, that is basically for ray tracing analysis, that will help to simulate the 3D optical element. So this module is basically the light incoupling and light outcoupling in solar cell and LED that can functionalize by complex 3D optical element or the surface texturing. Because the ray tracing module is there, this ray tracing module can be very helpful for surface texturing, where the planar surface is not there. There is some irregular shape, some different complicated structures are there. So that's why the texturing of the device, where different geometry can be textured by top or bottom of the electrodes. So this 3D optical element, Fresnel lens or other optical element, that can also be coupled with LED solar cell to improve the efficiency. Device surface, in effective solution with device light coupling. Laos can also model the optical output of chosen optical element with a powerful ray tracing algorithm, and it can also be integrated with soft set for light outcoupling geometry. Optical crosstalk, optical analysis for the crosstalk LED application, it is helpful. For optical crosstalk in given by the light and that is scattered inside the optical and leak the new pixel before the final release. So WOLED or AM OLED active matrix or different RGB pixel crosstalk or all the geometrical complex geometry can be simulated. You can see the Laos can capture the effect, capture the nature of pixel crosstalk, and that simulation suitable tool to optimize the characteristics of pixel matrix without costly or time consuming fabrication or testing process. That's why this virtual analysis will be there, and based on theoretical model parameter validation, you can predict your device characteristics. This is some different device, WOLED or some different planes. It is simulated and it will be plotted. In this optical analysis, since it is for ray tracing analysis, so either you want to simulate the curved shape liquid crystal related display application, AMOLED, LCD application, or pixel array application. It can be helpful for spatial or angular uniformity or luminance. This is also helpful for flexible thin film lightweight application, edge lighting. As you can see in the cell phone, due to the edge of the surface of the cell phone, there is some different effect maybe there. Some automotive car designings are there, quantum LEDs are there. So in this particular scenario, this tool will be very helpful to optimize the particular shape of your solar cell application. And by using this ray tracing analysis, you can see how much the light will get absorbed or refract and diffuse in your device. Now in this Laos, there are a couple of examples are there. Examples like AMOLED, active matrix, organic light emitting crosstalk. Example is already given to the beginner, how the beginner will start learning on the tool. AMOLED with crosstalk and different sections. Section in the sense the different segment. Z segment will be there. So the segment related active matrix OLED, basic OLED simulation without thermal effect, with thermal effect, OPB module, full module simulation where multiple cells are connected in the series, hexagonal type of metal geometry, finger grid, pixel crosstalk array, metal grid simulation. Participants, I request you kindly mute your mic. So metal grid with bits optimization of your device, series interconnected cells, solar concentrator or uniformity optimization, plain rectangular OLED, and so many more examples are there, or user can create different kind of other example in the tool. This software support on Windows, Linux, 10, 8, Ubuntu, CentOS. So basically i5 or i7 processor is good enough. With 8 GB also sufficient to run the calculation. If more is better, more hardware configuration is there in your computer, then definitely you will get a faster simulation speed. Multiple parallel processing on different cores. So job threadings are there, multiple processings can be simulated for different devices. You can also get 1 month trial version of the Setforce or Laos, whatever the tool convenient for you. Trial version can be provided so that you can see how this tool can be benefit. So before going to the trial version, you need to understand either this tool is really helpful in your particular domain, whatever you are working on. So accordingly, you can judge and let us know. We have so many YouTube videos are there, so you can visit our channel Fluxim or Impulse Technology, where a couple of videos on Fluxim website is also available. So that will help you to understand quickly for the new beginners. So scientific videos library, publication papers, manual, tutorial, example, and technical support in persons. In an online mode, we can also help you so that you will find, yes, this kind of product can help to boost your research in this particular optoelectronics domains. There are a couple of Laos tutorial are there already inbuilt with the software. Whenever you will install the software, you will find the list of tutorials that one by one, once you will follow it, you can also create different project by yourself. With all the manuals are there, numerical physical model implemented in the tool. In English, all are well explained with the example and online technical support that can also be provided by telecalling, by WhatsApp, by Google Meet. We usually available online so that user will satisfy before going to plan in the future. Even IIT Guwahati is already procured this Laos softwares. So this was basically a overview of Laos tool. What this tool will do, what kind of modules it consists, and what are the modules are divided, what will be the role of electrical module, thermal module, or optical module. Now, as I told in the presentation beginning, this set force is for one dimensional, Laos is for large area, crosstalk, PV module, and array simulation. This is one equipment. In the beginning, second slide, I inform about PIOS, that is for electrical optical characterization and impedance measurement with transients. For ELPL measurement, electroluminance, photoluminance, flows is there. For LITOS for stability of OLED and LITOS light for stability analysis of solar cell applications. So this is all about scientific product that our company is representing in India and supplying in India as well. For atomic scale modeling, nanomaterial, crystal, molecule, nano device simulation at atom-based device structure simulation, then we have this nano decal with their advanced version, rescue and their advanced version with QTCAT for quantum confinement, quantum technology, spin qubit device application. QTCAT tools are there. So you can judge which domain is more expertise you can gain in this particular domain. Accordingly, we can suggest you the better tool which will help to boost in your careers. So for atomic scale, nano decal and rescue are there. For quantum technology, qubit application, QTCAT tool are there. So this is all about brief presentation. If any participants will have any technical query or today or maybe after this webinar, you can note down my contact number. This is my contact information. So you can call me, email me. I can help you or reply in your email communications. This is my contact information. So thank you very much for giving your patience and listening the presentation session carefully. Sorry. Now I will go to the thank you page. So thank you very much. We'll go for the live session on the demonstration part where I will interact you with the tool, with the software, how it look like, what parameter input you can give, what parameter you can simulate and get your output device characteristics. So I would like to open my other application. Just a minute. So I'm sharing my web page of the screen so that you will get more information. Just a minute. So now you can see this web page that is called fluxim.com. I think my screen is visible. Fluxim.com, right? Okay, perfect. So these are different products that I explained in the presentation. Set first, Lyos, Pios, Philos, Litos, Litos, Light. If you would like to go in the detail, you can click on particular project. You can find the brochure, module information with their references of each product. Similarly, for introduction, electrical, thermal, and optical module with their references. Pios with their introduction, their module, and their references. With the information of all the product are given on the web page. If we talk about the publication, you can go to the research option and go to the publication options where you can find all the publication and collaborations. For this Laos, you can see I can go to this Laos and click on references. So you can see this is a reference option where some people are using, like Swansea University, they are using, and bottom of that you can find the publication of electrical crosstalk effect between different pixel. You can find this investigate papers, research paper, recent research paper on investigation of electrical crosstalk between different picture with high resolution or unique LED and micro display applications, including the solar cell application as well, and with different near infrared sensitive optical image sensors applications. Perovskite solar module application design and optimization. This paper is there. Some thesis. Color gamut changes by optical crosstalk in high resolution OLED, and some organic photovoltaic application for indoor applications. So these are all research paper. You can look into the papers later this presentation demonstration so that you will find many more things. You can see these are some modeling crosstalk or quantitative pixel crosstalk in AMOLED display or electrothermal simulation of large area device application. This is just for your kind information that all the information are available. So in details, you can look into our web page. And even YouTube channels are there where you can find some videos as well related to Fluxim Laos. So these are some research that videos are available. Once you will click on it in the form of videos, something you can find it related to around 9 papers, 9 videos are there. So you can look into these videos information. You can see these are all related video with this Laos and other set first applications. Now I would like to open the software. You can see my screen Laos 5.4.1. So I would like to right click and open as an administrator to give my background permission privileges. Now this is a graphical user interface of this Laos software. It is a completely user interface based tool. So there is no coding is required where you have no need to write any code or any script in the software. So you can find this user interface very easier or easy to learn. You will not find any difficulty. Either you are beginner or you are expert in the kind of software field. Apart from that, there is a help option are there where you can find some manual and tutorials. Manual where you will find the background physics, background models, background equations, on what equations the software will predict the device characteristics, what models are using, what equations are using, that are well explained in the manual page. So I click on this manual. You can find this is a Laos manual. Even after this webinar, those who are interested, I can share you this manual and tutorial link to all of you so that you can explore in the details, or if you will install the software, by default you will also get this manual and tutorial whenever you will install this Laos software. So this Laos is basically, as you already know, for design, optimization, simulation of large area, solar cell, OLED, module, PV, crosstalk and array applications. For background physics equations, you can see how much the electrical model, thermal module. So I can go down and step by step all the information are given. Either you want to take the information about physics equations, or you want to take the information about how to proceed to create different device structures or meshing. So you can see this is a one by one user interface information where anybody can go down and find, follow the step by step procedure, and easily it can be created. So within a week you can easily learn the capability of this tool. So the some topography view you can also import or generate or load in the object parameter file, some 3D Max file, DXF AutoCAD file, object file, STL file, and some different other extension you can import and export in the tool. You can see these are different geometry tapes so that you can get more light absorbed in your device study. Micro lenses array can also be simulated. That's why you can see the cylindrical array in topography import. Spherical lenses and other characteristics. And you can draw the geometry of your device. Predefined pixel topography and so many things are there. You can see this is generate pixel structure in topography import. Basically, to create the geometry, there is a software called LaborCAD. LaborCAD. This LaborCAD is basically an open source tool which will help to create the geometry. Open source tool where anybody can download and create the geometry of your solar cell. And that geometry can be uploaded in this Laos. Now you can see, apart from manual, tutorial option is there. The difference between the tutorial and manual is, manual will give you the background information. Tutorial will explain you the step-by-step procedure where you can create different kind of solar cell device simulation from scratch. So step-by-step procedure for creating or designing, modeling of the solar cell and do the simulation till the visualization of your output. That can be seen in the tutorial package. So that's why this tutorial package where proper screenshots are there. And I believe the user will get very easier once you will explore it or you will become familiar with this Laos tool. So you can see I can go up where couple of steps are there. If you want to simulate your first OLED, you can simulate your first OLED. You can import your geometry in the Laos. First PV simulation, first maybe PV module simulation, or case studies are there for OPV, AMOLED pixel crosstalk, optical crosstalk, and non-uniformity of emission in OLED lighting, OLED electrothermal simulation, solar concentration, electrical and thermal simulation. These are all tutorials. You can see how to create the geometry in lever tool and this type of geometry. You can see this is a hexagonal metal grid, and this hexagonal metal grid can be created for the for the geometry of your electrode. And if we can minimize the light reflection by using the electrode design, we can have a multiple option to create a suitable geometry of your electrode so that the losses can be minimized, and you can find the potential distribution inside it. So this DXF file of the geometry can be created in any create tool, and you can import in this Laos. This is a first example where if you want to simulate the first OLED, the everything starts from the geometry section where geometry of the device need to be created. Whatever wafers are there, whatever next depositions are there, or whatever implantation need to be done, or contact formation need to be defined, or biasing voltage you need to define. These are step-by-step procedure need to be done. That's why the first solar cell, first LED or pixel crosstalk, it can helpful create all of them in single tutorials. You can see, just follow it and you will be able to help. It will help you a lot for creating any kind of complex structure. Still, if you will have any problem, you will face any problem, you can also interact to us. We can help you so that you will understand your desired goal by using this tool. Now I would like to show the demo. In the demo part, you can see there is an option called new project. You can start from scratch, or you can also load the project from the library. If you want to start from scratch, you can click on the new. And here, once you will click on the new project, you can select either you want to create the project of your large area devices, or you want to start with the ray tracing applications. Accordingly, it will select the default path, or you can set the custom projects. You can set the name of project and select the location of your project where you want to save your project applications. And click on OK button. Once you click on it, you can find this is called the feature which the user need to give as an input. In this, you can see the geometry and meshing, device IVT, that is second feature, second tab. There is electrode tab is there. There is a boundary condition, ohmic type, Schottky type, or any different type of boundary condition. Swapping and optimization, where minimum and maximum of your swap value, variable value can be defined. Let's suppose you want to swap the thickness, then minimum and maximum you can set in the software. Software will perform the simulation on each and every biasing, and it will show at what particular bias voltage or whatever input you have taken. At that particular input value, you are getting the good output for that particular problem. So that's why the sweep option is there. There is option called optimization, fitting and optimization. You can fit the global fit optimization is there, local optimization algorithm is there. So this algorithm, I believe it will optimize your device structures. And there is solver are there which will solve your equations. Fully solver, simultaneous solver, direct solver, or direct spare solvers are there. Global solvers are there, non-linear solvers are there. Newton solver with line search, Powell dogleg, Leavenworth, Marquardt, and path continuation. These are different non-linear solver that will solve the device theoretical models equations. So user can define edge per the convenience. If I click on this geometry file, you can see the geometry need to be given either in the form of DXF, in the form of UNB Salom. There is a predefined rectangular geometry there, metal finger geometry available, metal strip geometry is available, rectangular metal grid, hexagonal metal grid. This is predefined geometry that already is available. DXF geometry file you can upload. It can be created by either in the CAD file or even in our software LaborCAD, that is open source tool where you can also create the geometry. And this Salom UNB format, some different wireless inside tool is there where some UNB application label, it can also get the input data. So for DXF file, select the DXF file and click on file option. Once you click on file option, since my software is installed in C drive, program file, Fluxim and Laos, this is a part of my project. I would like to go to the example. In the example, you can see the geometry need to be required. Either you can create from scratch in the LaborCAD and export in DXF format, that is freely available. If you don't have any LaborCAD tool, it can simply be installed from the website and anybody can install it. Even I can also help you to install the LaborCAD applications. Once you install the LaborCAD, then you can find this is called DXF file. It is called the geometry file of your device applications. So either you can take this 0 millimeter DXF file, 10 cross 10 centimeter DXF file, or hexagonal 100 cross 100 millimeter DXF file. Let's suppose I want to take this hexagonal 100 cross 100 millimeter dot DXF file. It's a simply a geometry file, so it can be uploaded. I can click on and click on open. Now you can see in this left side, right side, sorry, the geometry of the hexagonal DXF file that is created maybe in CAD tool or maybe in this our software LaborCAD. So here you can see this is called geometry. It is geometry. This is a geometry that you can see here. I can move it. I can click on the show geometry that will show you the geometry. So 0 to 100, 0 to 100. So 100 meter by 100 meter. This is geometry of your device. And the geometry is taken from the library. Now, if you want to simulate it, you can see there is predefined geometry one. That's why the feature show geometry is not given. Now to generate the mesh, there is a meshing tool that is called NetGen and BAMG. This is basically a mesh generator which will generate the mesh. Once the mesh is generated, NetGen mesh generator is there, and this BAMG is called bidimensional. I think anisotropic bidirectional anisotropic mesh generator is there. So I will select this mesh generator and then click on this run meshing. I can also set the minimum edge size, maximum size, or maximum number of vertices. It's called 50,000. So I click on this run meshing option. Mesh is going to be run. Mesh is running. It is in the progress. It may take very little bit time to generate or visualize the mesh. In the geometry, hexagonal metal geometry. So if there is some problem, then we can also minimize, we can increase the minimum edge size and maximum edge size. And then the maximum number of vertices will be reduced. If the number of vertices are increasing, minimum edge, maximal edge are very low, then the mesh will take some time to simulate it. It depends on your computer configurations also. My configuration is little bit low, but anyway, when you will decrease this vertices number, then you will get a faster mesh generation. So let's wait for 1 minute, then I can take another example and try to show you the mesh and some other input parameters. You can see the mesh size was very dense. That's why the mesh is taking a lot of times. Let me increase this minimal edge value. You can see the number of vertices that was previously 1 lakh or 11 lakh 36,911. That's why it was take a lot of time. So I have reduced the value from minimum edge to maximum edge size. And then I want to run the mesh. Now you can see the mesh has run because the number of vertices has been decreased around 17,597 mesh counts. So I can zoom it. You can see this is a max hexagonal metal grid and this is a triangular mesh. So hexagonal metal grid and triangular mesh is there. You can see this is around 34,765 triangle. If you want to simulate the mesh by using this anisotropic bidirectional mesh, then I can select and click on run button. This may be some different mesh, same triangular, but some size or some position may be different. So that's why two meshing tools are there. Now this is called mesh. Okay, once the mesh is done, then next you can see there is an option called device IBT. It means there is electrode, thermal coupling, device type, or simultaneous simulation type steady state, AC and excitations. So I can select the single electrode. So either you can select the single electrode or the coupled electrode between single and coupled. And there is option called thermal coupling with thermal effect, without temperature or thermal effect, heat generation only, full electrical plus thermal, both modules are there. Device OPV is there, and steady states and AC calculation. The results can come. And in the bottom of the page, you can find the electrical coupling in ohm, Montgomery, diode model, inputted JV, JVT. These are all results from one dimensional as well as whatever third party other tools are there. So I click on import JVT. Once I imported, you can see in the slide side, the color has been changed. The mesh has been assigned. Full electrical thermal coupling is done. And then after applying the device IBT, current voltage, single electrode type, thermal coupling or
Excuse me, sir. You are not audible, sir.
Mic is mute. Sir, your mic is mute. See in the meet.
Sir, are we audible?
now is it okay?
Yes, sir.
Yes, sir.
Okay, fine. So here you can define, how the device is formed. The device will start scratch from the geometry. Once the geometry is created, so how the geometry will be created? Either you can take the DXF file or you can take the default geometry given in this layout. And once the geometry is done, you can see these are multiple options for the geometry. The next geometry option is called meshing, where you can define the vertical mesh or that number of mesh points, node points, vertices can be defined. Then third tab is called where you can set the electrode type, single electrode or coupled electrode, thermal annealing, thermal coupling or without heat temperature effect, and select the type of device, LED type or solar cell type, and steady state simulation, AC simulation. So DC, AC, transient all are there. You can see this is called, you can import the characteristics, import the, hello. You can import the one-dimensional current voltage curve as well. You can see this is called import data, where from SatForce you can import the JV data characteristics, not only from SatForce, from any tool. You can select it, import JV curve, and you can import your graph here. So the JV curve need to be imported here, and we have to select the file, then it will display. One minute. I will take in the example, and this is electrode type where top and bottom electrode, and more electrode if you want to define, simply you can click on this and you can restore your electrode type. And this is called boundary setting, where you can set the boundary top edge of bottom edge of the boundary conditions. So if I select it, this first option, it will say here, this is called the red color bottom edge. It is called the bottom edge current electrical type. And if you will select it, you can see this is called vertical red color edge. It is for the top device. Top, you have to assume it in the 3D. It is top device, left, bottom, or which edge is there for the top of the device. So that's why it is showing the direction on the top boundary condition. And this is sweep, where you can also do the sweeping and optimization, where you have to enable the sweeping. And you can add the sweeping here by clicking on this line, and you can define the input sweeping value. Either you are sweeping the thickness, you are sweeping the voltage, current, or whatever input you will sweep, that you have to select from this conditional. Just a minute. One minute, sorry. Am I audible?
Yes, sir.
Okay. So I would like to import some existing project. I go to the import from zip file. And since the software location inside my C drive and Fluxim folder, and this Laos example, I will go there and go to the tutorial. This is existing tutorial. So for that, let me take one AMOLED crosstalk. I will open. It will load here. Now you can see here.
technical issues, we will be taking a short break. We'll take it with the chat and we'll start it.
Am I audible now?
Marlboro Fit.
And my screen is visible?
Yes.
Okay, perfect. So let me go there. So what I did, let me start from beginning. So I import the projects. I click on file and import from zip file. So I want to take OM OLED. I can take any solar cell also. So I click on open it and let me overwrite with the existing project. So this is one pixel crosstalk where blue pixel will be there in in this geometry. Some of them are red pixel, some of them are blue pixel, some of them are green pixel. So DXF geometry file we have imported. It is in micrometer units. We can also define some defect or geometry we can create it. If I click on this device IBT, this is a coupled electrode device simulation with OLED type without coupling. If I select on this blue pixel, you can see this is red one. Vertical lines is called the blue pixel lines. This small one is called the green pixel lines. And third one is called the red pixel. This is called the red pixel box. So rectangular box is called red pixel. If you would like to visualize the graph, simply click on the blue pixel graph. It will plot the current density plot of this blue pixel. Similarly, for anything you want to plot the green pixel or you want to plot the red pixel. So this graph you can visualize for current density, JV curve. And bottom of the page you can see here we have uploaded the IB of this red pixel, green pixel and blue pixels. There is option called browse. In the browse we can browse the IB data. This is called JB curve of dark, light, green, OLED. Whatever data you want to browse for this data, it can be browsed. Unit and current density value you can plot. So under light or under dark condition, you can plot your device efficiency. And this is called electrode type. You can see. This is electrode, default electrode. If you want to see the blue pixel electrode type on the top and bottom will also be there because it is not visualized in the 3D. It is 2D structure, but heat resistance are defined for 2D and 3D both. So these are all pixels. And for green pixel, once you select it, you can visualize it. And boundary condition, you can find the boundary condition for all the pixels either on top side or in the bottom side. The boundary conditions are set. That's why the color are changing respectively. And there is a swapping option is there where we are swapping the blue pixel voltage vising. It is swapping from 0 volt to 5 volt with the increment of 0.1 volt linearly. There is option called linearly, logarithmic or tabular. So it is swapping from 0 to 5 with 0.1 increment. So swapping will help you to optimize your device structure. Not only a blue pixel potential you can swap. You can swap the boundary condition, potential, temperature, electric current, thermal flux, or any other stack thickness, dark saturation current, ISC, conductivity, temperature. These are all input parameter swapping options where whatever the parameters are unknown for you, you can set the minima and maxima. And in between maxima and minima, you will find the more accurate characteristics. Software will give the simulation on multiple value between minima and maxima, and you can find the peak on exact particular value. That's why the blue pixel age, you can see the blue pixel potential are increased from 0 volt to 5 volt with an increment of 0.1. So software will do the simulation at 0 volt, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 up to 5 volt. It will run the calculation and you can find either you are getting the good output at 2 volt, 2.3 volt or 2.7 volt. Whatever the voltage you are getting the output, you can select it. And this is for optimization and fitting, global optimization or local optimization with imported JV curve, minima and maxima optimization. It is basically iteration control, which can control iteration and optimize your characteristics. And to select the solver, this is to select the solver and control the performance or memory trade-off by selecting the required features of the solvers. You can see there are some of non-linear Newton solvers, Newton solver with line search, Pobel, Lindbergh, whatever the search option is there. Now I want to basically run the mesh and then we'll run the job. So simulation can be run from here. So before, since I run it in the morning, so I click on this result tab. This is result tab. So let me run it again. So by clicking on this run button, you can run the job. Now simulation is running, that you can see. The simulation is running. It will solving the equations. Software is very fast in converge. It will try to converge the equations default based on default parameter and it will plot your output. You can see the result window has been enabled and it has plotted the total device current diagram. This is potential that we have applied from 0 volt to 5 volt. So if I will zoom it this particular point, it will increase from 0 volt. But you can see here this one at 0 volt how much nearly you are getting the currents. Okay, and at what particular value the device current is like going down. So 0 to 5 volt we have given as an input and you have to check at what particular voicing the device is going to be decreased. You can take the cursor on particular location and it will plot the potential as well as device current. So this is total device current. You can see with respect to x-axis, x log, y log, or in the form of logarithmic or without logarithmic also. This is without logarithmic. If you want to see the total ohmic losses, just click on this total top ohmic losses, and this is top ohmic loss output characteristics with respect to the changing of potential from 0 to 5 volt with 0.1 increment. That's why with the dotted lines are there with every 0.1 increment it is giving the dot, and you can take the cursor and it will give the value on that particular point. Now you can see this is a global data. Here you can see the total device current, ohmic loss, top electrode, ohmic loss, bottom electrode. If I click on the solar cell, you can find the maximum power point, maximum power, open circuit voltage since it is LED application, fill factor and other boundary condition flex and other things. For ohmic loss, bottom diagram, and this is for top diagram. So top and bottom ohmic loss diagram you can see and check the variation in the losses for the top electrode and bottom electrode. That's why these two graphs are there. Source power diagram. Once you click on it, it will plot the source power diagram. This is source power diagram. Only since as a input we have sweep only the potential. So that's why the potential respect all output are plotting. This is total power diagram. Now you can see this is without any pixel. Okay. If you want to simulate, you want to see your results on the pixel data. Then you can see the diagram per subdomain. So blue pixel diagram subdomain, diagram per subdomain, electrode pixel, blue pixel, electrode pixel, red pixel, boundary condition. Also at each voltage wise, potential applied on boundary condition, age, blue pixel on bottom electrode, voltage equal to 0. So based on 0 voltage, you can see your pixel, blue pixel data characteristics, because this type of geometry box that pixel were created. So at 0 volt, you can see these all characteristics. Either you want to see the potential. So I double click on this potential for bottom electrode. You can find the potential. If you want to see for top electrode potential, this is for top electrode. Source current density for the top electrode. Ohmic losses for top electrode. You can also zoom particular region so that you can visualize it properly. I can scroll it and make it on the home so that I can see the ohmic losses top electrode and with the graphical representations so that you can identify and calculate, because this losses and this average or scaling window is there, scaling line is there, which can help you to find the losses due to the top electrode. Similarly, for the ohmic losses, bottom electrode, because top electrode is different and bottom electrode is different. And this is all source power at top electrode, total power at top electrode, This is total power at top electrode, in plane current top electrode, in plane current at bottom electrode, potential difference between top electrodes. And you can publish your data accordingly. You can create your type of geometry. So these are all data at zero voltage Vc. You can see there are multiple graphs are plotted at 0 volt, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. All the graph which I have shown you just now on different voltage Vc, multiple output file is generated from 0 volt to 0 volt to 5 volt with 0.1 increment. If you want to see your data at 1 volt, I can double click on it. You can see this is data and with scaling layer. Similarly, click on is at 1 volt and find it and calculate the value of your particular that pixel. The geometry may be different. You can create your geometry according to your convenient. You can import or take the inbuilt geometry builder and find its characteristics. You may take different other conditions. Similarly, this is for only blue pixel characteristics. If you want to plot on other characteristics on other pixel, then you can also able to plot. So this is blue pixel on bottom electrode, potential on top. And you can also see the total device current, ohmic loss, top electrode, ohmic loss, bottom electrode, in watt, source power, total power, electrode area, luminosity. So that's why this all are there. So that's why this result window will help you to show all these things. I would like to take another example that may clarify other maybe doubt. So I click on this import from GIF. Let's say take another tutorial. I can take optical pixel crosstalk as an example. This is one optical crosstalk example where we have taken the optical crosstalk input parameters. So where the layer thickness, encapsulation layer, and their all input parameters are defined. Let me run the job because it is for optical analysis, not for electrical or thermal. Now simulation is running. You can see the ray tracing analysis for optical crosstalk is going to be performed. Now the simulation is completed and results window is enabled. So I can click on this polar plot theta pi with sum over all xy coordinate. So this is polar graph where irradiance is calculated. So positive theta, if you want to see the negative theta, it is also generating the plot at negative theta polar plot. This is at negative theta value irradiance. Similarly, all other xy plot for top emitting, bottom emitting, far field, color plot, all are there. This is at xy plot with top emitting. So which pixel it will calculate? It is a far field color plate is there. You can see the surface with the edge, surface with the wireframe and other. You can see also the movable detector sample array on different wavelengths, retracing wavelengths. This is detector 3D view. You can see this is detector 3D view, where this is called pixels. This one, this 4 is called pixels, where uppermost or detector bits, detector height, that can be seen. And this is sample array. How the light will get on the top for optical analysis, how the light will enter on the device and it will reflect from the device. So that study need to be done. So this is detected wavelengths, at what wavelength you are getting the bad or detected, which one is called bad wavelength, which one is called the killed wavelength, which one is called the absorbed wavelength. So accordingly, you can see the killed, absorbed, or detected wavelength regions. Now, similarly, I want to take another example. These are all set force laws. Integration is also possible. Full PV module simulation, OPV simulation example, electrical AC simulation, basic OLED without crosstalk, basic OLED with thermal applications, crosstalk with different sections, interconnected series cells, solar concentrator, uniformity. So let's suppose you want to simulate some different OPV. Let's suppose a series interconnected cell for PV devices. You can see this is a multiple cells connected in series. That's why this is geometry. This geometry. I can show the geometry and run the mesh. This is mesh which is generated in triangular form. This mesh. And this is different like device electrode type, ohmic type or other type. Accordingly, it is selected the required input parameter. Steady state AC and excitation frequency we can set. It is a type of electrode where the electrode position is defined, bottom side or top side, and boundary condition. This is the boundary condition that need to be seen. You can see the red color represent the boundary condition here. This red one for top and bottom. And this sweep again, it is taken the voltage potential from minus 0.2 to plus 2.2. This time from negative biasing to positive biasing. So minus 0.2 plus 2.2 with 0.2 increment. So minus 0.2, 0, 0.2, 0.4, 0.6, 0.8, 1. Like that, it will simulate and show your output. So let me run for this particular example. Simulation is running. It is done. Calculation is done. And the results are generated. Total device current, total ohmic loss, bottom ohmic loss, source power, total power, and if any subdomain results are there, it will also display. Now you can see that different potential applied boundary condition results are there at 0 volt, minus 0.2 volt, 0 volt, 0.2, 0.4, 0.6, 0.8. So different biasing, it will plot your results. You can see this is a graph for the solar concentrator. And find the concentration is automatically calculated. Electrode area, total power, source power, and solar cell data can also be collected if it is there. This is difference. Now you can see at 0.2 volt. This is solar cell characteristic data. Maximum power point is calculated. Maximum power per area, open circuit voltage, short circuit current, fill factor, linearly interpolated value, and SP line interpolated value. Accordingly, 0.2 volt, the data is calculated. If you want to see this data at 0.4, the data will become change. Something may be difference. So different voltage applying biasing, the maximum power, fill factor, open circuit voltage, or whatever it is, it will change it. You can see the fill factor at 0.4 is 4.5. If you want to see at this value 2.2, it may be something. If it is changing, then it will reflect here. If it is not changing, then maybe it can be same value. So these are all device characteristics output. And some brief idea, very presentation and demonstration is given. This is command line, command log window. If any error is there during the calculation or how much time it's taken, that will display in this command log output file. It is a calculation log tab where once you will click on it, it will show which equation, how much time, or how the job is done. Is it the device parameter got converged, or how the convergence accuracy. So that's why this convergence simulation result will show the output, all your output, and project property will give as an input. This is input, this is calculation log, and this is output. These are three major important. In the property project, geometry and meshing is the important, then device input parameter, electrode, boundary condition, and optimization by swapping the parameters. And software will do the calculation in each value. So basically this device can help to overcome the losses, and it will simulate the large area, PV module, LED, pixel, crosstalk, or whatever other application you want to simulate. You can see there are a lot of other options are there. These all examples are available already. This is hexagonal metal grade example. Let me run it. If you want to see the defect, you can see the defect option is also there. You can enable the defect, number of defect you can enable, seed for the defect width, defect height. So defect can be increased, or predefined geometry, radius, metal grade fingers. Now I want to run it. Simulation is running, full Newton solver is executing, calculation is done. You can see the simulation is running on the bottom. If you want to kill it, the simulation can also be run. How much memory, how much percentage the simulation is done or CPU is utilized, that will show here. So you can get to know about the progress of your simulation. And this is linearly interpolated data of maximum power point, maximum power per area diagram, fill factor data, open circuit voltage. So linearly and spline data is there, and you can plot all the characteristics according to the convenient. So from my side, I have given the overview about the tool. So if participants have any questions, I request you can unmute your mic and please put up your questions. So thank you very much from my side. I have tried to explain a lot of things, but once you will explore the tool, then you will have a much clear idea. And if need more in detail, then we can also have a more discussion in future.
Okay, thank you, sir, for your talk. So here in the chat box, we have a question from the attendees, like, can we use now software for CIGS solar cell and how it is different from SCAPS?
So SCAPS is only a one-dimensional simulation where mass cannot be defined. Final element method is not possible because FEM will solve the equations on particular node point. That is not possible in that SCAPS tool. SCAPS tool is basically a similar to SetForce, where it will work on only one dimensional. Two dimensional is not possible. Only 5 layer or maybe maximum 7 layers can be simulated. Whenever you will go beyond that, then it will not be possible in that. So for micro level simulation, whenever the device size increases, then this SCAPS software fail to converge. It will not get it converged. In this case, this loss will come in the picture where when you are applying some high temperature or the geometry of the device electrode is not increasing the device efficiency, then optimization is important of the geometry. So geometry cannot be optimized as it can be optimized in this loss. So this is like next generation of escape bundy. Escape bundy and setforce both are similar, but whenever we will go in the upcoming future from cell to the module. Now people have started a lot of works have been done on solar cells. Now many people will switch to work on module simulation, interconnected cells. Then SCAPS cannot do that. Where Laos software will be do because it can perform the module algorithm is there, which is implemented. It will simulate the PV modules. Array cannot be simulated, crosstalk cannot be simulated, and many more advanced large area level the device which the Laos can handle that FCAPS cannot do that. So these are two different next generation tool Laos from the FCAPS Bundy.
So thank you very much. So with this, we are concluding today's session. Thank you everyone for your active participation. Please join us tomorrow morning at 10 a.m. for the last day of the online familiarization workshop. Thank you everyone.
So thank you very much to all the participants. If anybody interested in getting the trial version, they do let us know. We can also help you in that. And some 50 licenses already given to INUP organizer. You can also contact them. Thank you.
Just thanks.
Okay, and for any further query, you can keep on chatting in the chat box.
I have mentioned my email ID on the chat box. So if anybody want to reach me, they can contact me. My email ID is given in the chat box. Thank you very much.
Sure, sir.
Yeah, thanks a lot.
Yes,